was hoping so. This is the good part. You guys ready for the good stuff? This is the good stuff. Woo. You know why it's good stuff? It's got cool words in it, man. It's got words like fundamental and theorem and calculus. Oh. We're going to talk about the fundamental theorem of calculus. Oh. That's right.
I'd really like to see what your weekend consists of. Just like in front of the mirror doing all this stuff.
When I go to the gym to get my pump, I just go, derivative! That's it? No, that's not true.
Maybe that kid that you kicked out.
Not good.
Almost the whole semester, we're just making the theorem of calculus.
Yeah, basically. Here's what you know so far. You know that this is an area. You also know how to calculate indefinite integrals. You know how to calculate them like this. That this was capital F of x plus c. Remember the plus c part, all doing that? We know how to do integrals. We've done that already. Here's what this represents though. What this says is, okay, an integral represents an area. This is the antiderivative, but what do we do with that plus c? Let's talk about that for right now, and then we'll have a really good picture of what's going on. So here's our, I'll use the same graph I have over there. Here's our graph, and this is f of x. We're looking for the area. What we want to do is find the area from A to B. That's the goal, without using our Riemann sums or the summation notation. We don't want to do that. We want to really just think of this as an integral because we know an integral geometrically represents the area. So how can we go from this picture and this thing and tie it all together? What we want is the area from A to B. Here's how we're going to think of it. We're going to think of it as, well, how about this? Could you find the distance from A to B? How would you do it? You would do B minus A. If this was 10 and that was 3, you'd do 10 minus 3, right? We're going to do basically the same thing. We're going to say, let's take the area up to B minus the area up to A. Would that make sense to you? We'll take all of this area minus off all of this area. No matter where you start, that would work for you. Would you agree? We'll take all the area from left to right, all the area, no matter where we start, up to B, and subtract off all the area up to A, and that would leave us with this little bit. How many people buy into that, feel okay with it? That's exactly what we're going to do. So we'll take the area up to B,
Starting from infinity?
starting from wherever you want. It does not matter, as long as you start the same.
One for both.
Yeah.
But then you just make the exit point A.
See what?
Can you just make your starting point A, which so you and figure out the area to B and subtract 0?
Well, I have to give you something that this makes sense, right? And the way to do that, we are going to start at A and go to B, but find the actual. You can see why we have this next piece in there. Right now, if I give it to you, you'll probably follow it, but I want you to understand the concept of why we have a subtraction in this at all. Okay, and we're going to have one right now. So let's think of it. So the area is, this is not changing. The area is this. What we're going to do is take the area up to B minus the area up to A. Now here's what you have to realize. What we're doing here is calculating the area function. Do you remember me introducing that to you a long time ago? That this indefinite integral actually is an area function, it was a family of curves. We just didn't know which one it was. Well, if we have that family of curves and we're going to an actual point that says this is where you're going, you're stopping here, that solidifies it for you. It's no longer indefinite, it's definite. You're starting at one point, you're stopping at another point. So this right here, that's an area function, and we actually have something to plug into it. We have the point, well, where are we stopping? The area up to B, you find the area by plugging in B. The area up to A, you find the area by plugging in A. So the area from A to B is the area up to B. The area up to B. That would include wherever your starting point is for area, that would include everything up to the point B. Everything above the x-axis to the point B, you got me? And then we'd subtract off this point A. Now really what we'd consider is starting from 0. That way we're not being silly about it and going way too far. We'd say, let's just go from 0, okay? You'd have this area minus this area, it'd give you what's remaining. The area up to B, plug in B. The area up to A, plug in A. That's how you do a definite interval. You find the antiderivative and you plug in your bounds. It's actually that easy. Not bad? Not bad. No, come on, now there's one question out there. What's the question? Come on, do you see it?
What do you do with C?
Oh, good. Do you see it? Ha 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 ha. Where's the C? By the way, this right here, this statement is the fundamental theorem of calculus part 2. I'll give you part 1 later. Fundamental theorem of calculus
F
part 2. What happens to the C? Oh dear, why don't we have a C? Why not?
Now you know definitely what it's going to.
Well, you do know definitely, so we shouldn't have a C, but when you think about it, remember when we're finding out this right here? This is a family of curves, right? How are you supposed to know where it's at? Wouldn't a curve way up here have a different area than one right here? Clearly, the height would be different. So why does this even work? Well, think about this for a second. What about the C? What about C? Suppose you considered it. By the way that you write this, I should actually give it to you this way. One more thing, this is also written. As f of x. That's an evaluation symbol from A to B. That's how you can write that, and we're going to be practicing that as well. It says the same thing, okay? This and this is the same. How you do this is you plug in B and you subtract off A. You plugged in B to your antiderivative and you subtracted off f of A. Are you guys okay with the notation? So when you see that line right there, it's like half a bracket, goes from A to B, that's what that means. So if this equals this, and this equals this, let's suppose that we actually included the C. Now some of you might be wondering, well when you think about it, you might be wondering, why don't we have a C1 and a C2? Say it again.
They're the same constant.
Why are they the same constant? How do we know that for sure? He's right. Why? Say it louder.
They're from the same country.
They're from the same function. If you're integrating that same function, you're not switching functions on me, are you? Integrating the same thing. Then whatever c you get is your c. No matter what you're plugging in, that's going to be the same function itself. Does that make sense? So wherever you're at, that's the same function. So we integrated one time, look what's going to happen. If you have f of b plus c, it's not c1, it's just c. F of a plus c is not c2, it's just c. What's going to happen to my c's? Wherever your c is, that height difference will be eliminated. It drops out of your equation, as your book likes to call it. The c's are gone. So remember, the plus c, that's just the height, right? Height of your function. Even if it's way up here, same type of function, just way up there. But both of them would be way up there. The f of b plus c, f of a plus c, we're subtracting out that plus c part. The plus c's will be eliminated from your equation. And that's how we get what we get. So the c is gone, drops out, so we don't write it for our definite integrals. Indefinite, absolutely. But definite, we should end with a number, end with an area, because this thing is an area. By a show of hands, how many people feel okay with what we talked about so far today? Would you like to try a couple examples? You're going to really like these, by the way. Are you ready to really like something
Yes.
in this class?
It's been a while.
Oh.
After that this weekend's homework. Great, now we're on our fail.
Yep. You're sunk now.
Welcome to that really transcendental.
Exactly. Okay, so an integral from 1 to 5 of x dx. This is an area, which means we should end with a number. It's actually a definite integral. Why is it a definite integral and not an indefinite integral?
Constraints.
Right there. There are bounds of integration. We actually have numbers. We should end with an area. Now, can you integrate x dx? Easily. Yeah, we already did that. No need for limits. No need for any of that stuff that you spent your whole life doing just now, okay? It's doable. You did it, right? But this is a shortcut, not a shortcut. I guess it's a shortcut to doing it. What is the integral of x, please? Where are we integrating from? Where do we start our area? Where do we stop our area? 1 to 5. Why don't we have a plus c here?
Because we have low.
Even if it fell out. Even if we did, it's gone because you can subtract it off anyway. It's the same plus c. 1 to 5. Here's how you show your work. You do this step first. You show me what your integral is. You show me where you are plugging in numbers from. You plug in the top one first, subtract, then plug in the bottom one. This would be 5 squared over 2 minus 1 squared over 2 is how you show that. Do you see where the 5 and the 1 are coming from? So we're going to get 25 halves minus 1 half. How much is that? 12. Yeah, 24 halves is 12. Is that quicker than a Riemann sum? All the stuff you can do in left endpoints?
Yeah.
What is 12? What's 12?
Area.
That's exactly right. Area under that curve, which is just a diagonal line, from 1 to 5.
Yeah. Thanks.
You're welcome. Well, the other stuff is good to know. It shows you where it's coming from. It shows you why you're doing it. It shows you how you do it, and you make sure you know what all this stuff means, right? If I just gave you that, you could do it, but you'd have no way, you would not understand it. We did the limits of the sums so you would understand why you do this, how you do this. Now, we needed something else, though, because when we get to things like this, a Riemann sum doesn't work all that nice for that. Maybe we'll do an integral with that. So this is also an area. It's an area from 0 to pi over 2 of cosine x. That's your cosine curve. Now, the integral of cosine x, you've got to be able to get these right, otherwise your areas are going to be wrong. You'd show an area above the x-axis when it's below, or below when it's actually above. What is the integral of cosine x, please? Do you need to memorize that?
Yes.
Yep. And where are we going?
Between 0 and 5,
Which one do we plug in first, the pi over 2 or the 0?
0.
Wait, which one?
5 over 2.
The pi over 2. Otherwise, you'd have negative, which, by the way, if you notice that, when your bounds are reversed, notice how you're subtracting off the wrong thing? That would switch your sign of your area, right? That's why the property I gave you where you can switch your bounds and it switches the sign of your integral, that's why that comes about. So here you'd have sine pi over 2 minus sine of 0. All right, come on now, people. I know you love some trig functions. Throw it at me. 1. Which one's 1? 1 minus
0
equals
1.
your area is 1. That's weird. Oh my gosh, have you thought of this, what this is? Do you understand what this is?
Yeah.
What's the picture?
Yeah. And you're just picking one of those spots.
Starts here, goes like that. Here, there. Right? Hope so.
That's wrong. That's a
That's cosine starts
the
there.
function cosine. Right.
Cosine. Cosine goes to,
Yeah.
oh, I'll have to erase it to draw a better picture. Did you have questions on that?
Nope, I'm good.
Watch the video. On what? You just found, yeah, don't draw these first, draw your curve first. Shoot, come on now. So teach you a master's degree. Yeah. Yeah, that's your area that you just found, that's equal to 1. Isn't that very interesting? That's interesting. It really is interesting.
Which means the next section would be equal to -1.
Hopefully -1.
And then it'd be like positive, so on and so forth.
Positive 1, -1, -1, positive 1.
Okay. And then it'd be +1, so it all.
Add it all up?
0.
Yes.
Okay. Is that just
Which
true?
means the area of a circle is 0. Did you catch that? Wouldn't it be if you did an integral?
Yeah.
Yeah, because you have the area above and the area below would match up. Because we're talking about net signed area right now. We haven't made it to total area, which is what we'll do in just a little while. We haven't made it there yet. Total area would change the area below the x-axis into something above the x-axis so you can actually add it together. We'll talk about that in just a bit. Right now we'll do a couple more examples just to really illustrate this stuff, and then we'll go till the next class.
Now, always adding up to 0. Is that still true for also tangent?
No, tangent has undefined points. You can't go further.
Okay.
If you think about tangent,
Yeah.
tangent does this. Also one that would probably be kind of hard with Riemann sum and those limits, okay? Not one that's great. However, can we do integrals with it? Sure, sure. You tell me what you do first.
You can't split that.
Why can't you split that up?
Multiplication.
Ah, darn it.
I get rid of your square root, turn it into what, x over 1/2.
X to the 1/2.
Then I would.
That'd be a good idea.
Then I'd combine the two, and then you can do your standard integration.
Sure. Don't jump to something super hard right away. Don't jump to a substitution. I haven't showed you that for this yet, right? So that's off the table right now. Don't jump to that stuff. See if you can do it easily. Make sure you maybe change a root or two. Substitutions often work when you have, well, trig functions is a good indication for that you should probably try. Or if you have parentheses, that's a really good indication you should probably try. And it won't distribute nicely. That's a very good indication you should probably try. So, x to the 1/2, yeah, I'll bind to that, dx, I like that. And combine them. X to the how much if we combine those?
One.
You add, right?
You add, so it's 5/2. 2 plus 1. I got a calculator.
X to the 5 halves, yes?
Yeah.
Can you take an integral of x to the 5 halves? Very easily. This would be x to the 7 halves over 7 halves. Over the same exact variable. No, I'm sorry, exponent. Exponent up top, exponent on the bottom. No problem. Make it a little bit prettier here. We're going to have 2x to the 7 halves over 7. And then we get to evaluate from 4 to 9. We plug in the 9 first. I've actually given you some nice numbers. Do you know how to do 7 halves without a calculator? Or to make it quicker on the calculator? This is power over root, right? Oh geez, I hope so. Do you remember that? Power over root? So you can take either one, whatever you want first. I would take a square root of 9. Square root of 9 is 3 to the 7th. That's what you plug in your calculator. I can't do that in my head. That's a pretty big number. 3 to the 7th is huge. So this is 2 times, someone tell me what 9 to the 7 halves is, or 3 to the 7th. How much? Minus. This is the square root of 4 is 2. Then you do 2 to the 7th. How much is 2 to the 7th? Are you okay on getting those numbers out, ladies and gentlemen? 2 times 2,187 is what?
4374.
This should be 256. Someone give me, since we already have a common denominator, someone give me 4,374 minus 256, please.
4118.
Does that simplify it all? That's not divisible by 7? Then you leave it. You could do a decimal if you really wanted to. Let's make sure before we end this that our math is correct. Can I get a double check on 2187?
Yeah.
You got that as well?
That's
Can I get a double check on the 128?
same thing.
Same thing here as well? All right, how many people feel okay with what we talked about so far? Awesome, we'll try a couple more examples. We're almost done with our definite integrals.
That is so much.
All right, well, what do you say we continue some examples? Here up here we got the integral from 0 to pi over 3 of secant squared x dx. Now, we don't have any substitution for definite integrals yet. I'm going to show you something about that in a little bit. So right now, everything basically has to fit our integration table. What we learned last time was that when we do an integral like this, a definite integral, we found out firstly how to do it, and secondly, that's exactly like finding the area with the Riemann sum, or the sum of those partitions, which is very nice, very, very nice. So let's go ahead and let's take the integral of secant squared x dx. Do you all remember the integral of secant squared x dx? Tangent. Tangent squared or just tangent? Good. So here's how you write that. You'd say, okay, I know this is tan x plus c or not. If it has bounds, no, because you're going to find an actual area. Because what you're going to do right now is you're going to be subtracting f of b minus f of a, and if those did include c, it'd be the same c, they would drop out of your equation anyway. So no, we don't have a plus c on this. What you do is you have this first, and then you throw up, you don't throw up, sorry, that's it when you go home for your homework. You put up the integration, or sorry, the evaluation symbol. You go, okay, I'm evaluating from 0 to pi over 3. So therefore, you show me what the integral is, you show me your bounds of integration, your bounds of evaluation, and then you plug them in. Which one do you plug in first, 0 or the pi over 3? Okay. So what this says is tangent of pi over 3 minus tangent of 0. Well, that's not too painful. How much is tan pi over 3? Don't leave me hanging. Awesome. 1.73, like my calculator says. Yeah, okay, very good. Learn a unit circle. Root 3. Root 3 over 2 divided by 1/2. Reciprocate, multiply, you get root 3. That's because it's sine over cosine. You need to know that. Okay, anyway, so we have our integral, the area underneath the curve of secant squared between 0 and pi over 3 is, we got it, square root of 3. It's interesting, right? It's kind of weird that we're able to find those areas so nice and neatly. Are you ready to try a couple more of these things? Yes, no?
Yes.
Did that make sense to you? Besides the square root of 3, which you all just kind of screwed up right now? All right.
You have so much faith in this one.
Hey, you're the one who screwed up, not me. Okay, explain to me something about this problem.
You have to invert it and then change it to negative integral of,
Okay, very good. Explain why. What's wrong with this problem?
it's backwards, the bounds are backwards.
It is. It should go from smaller to larger bounds. In fact, you know what? If you did it like this, if you did, you would get, I believe you get the right answer actually. If you try it right now, you'll get the right answer. But that proves the statement that we made before, that this is going to be negative. So for instance, if you did this, you'd get x to the 4th over 4, right? No plus c. But if you evaluated from 4 to 0 like it says, you'd have 0 to the 4th over 4 minus 4 to the 4th over 4. And what that would end up being is negative 4 to the 4th over 4. So 4 cubed, negative 64.
So,
If I've done my math correct. Did I do my math correct?
Yeah.
Yeah. Now let's check to see if we get the right answer the other way as well. We also knew from a property that if I reverse this and go 0 to 4, that becomes a negative. Well, let's see. That would be negative x to the 4th over 4. That would be negative. You need brackets there because you're going to have a sign in the middle of that. And that's evaluated from 0 to 4. 4 to the 4th over 4 minus 0 to the 4th over 4. And that would give you negative 64. Negative 64. Which by example kind of proves that that was true, that I can reverse my bounds, and that makes me change my sign. So just by an example, we see that that is true. But notice how you do actually get the same exact answer either way. That's because it is true. It has to be. What it represents, though, is kind of awkward, because this looks like it's an area above the x-axis, when in fact it's not. This is just read wrongly, incorrectly. So the correct way to do this problem would be to write the bounds in the appropriate order with the negative out in front of it, and that would give you negative 64. Either way, but this is kind of showing you, okay, this is an area underneath the x-axis, not above it. How many will feel okay with that one? Okay. Oh, lost it.
Bring the x squared to the top.
Okay, we could bring the x squared to the top. Now what?
Negative 1 is negative, there we go.
There we go.
Could figure out how to say it, but.
Okay, all right. You'd have negative 1 over 1 minus negative 1 over negative 1. Yes, no? Hopefully, if I did that right, make sure my signs are correct. I'm looking at that as negative 1 over 1 minus negative 1 over negative 1. That's negative 1 minus 1. Negative 2? You get an answer. You do. But now, think about the answer.
I can have a negative area.
Well, you can have a negative area, it would mean it's underneath the x-axis.
Oh,
That'd be okay. Think about the function then. Graph it on your graphing calculator if you can't think of the function.
It's a domain area,
Why?
because it's negative.
No, not because it's negative. Think about the function. What's the function do? I don't want to draw it in crayon for you. Think about what the function actually does. We have done so much in this class for you not to know this.
As asymptote.
Say what?
As an asymptote.
Where does it have an asymptote?
That's x goes to infinity.
Okay, it does have those. That's okay though, because I'm between -1 and 1. I'm between that.
And it's-
Draw the graph if you have to. Draw it. You should know the shape of that graph. You really should. Okay, you're gonna make me do it. You're gonna make me. Oh my gosh. Plug in 0.
No, it has, yeah, it has to.
Plug in 0. Plug in 0. Can you plug in 0?
No.
Why not? So what's it tell you at x equals 0? What do you have?
Another asymptote.
Look at your bounds. Where do they start?
On each side.
Okay, so are you adding up areas that actually are undefined at 0?
Yeah.
So it says you're making rectangles. One of those rectangles is going to infinity. Do you see it? There's probably infinitely many of them are going to infinity because when you go that close, you're going to infinity anyway. So can you actually add the area? Even though you can do the work, that doesn't exist. There's a theorem in calculus. I don't think I get to it, but basically it says that if you're not bounded somewhere, if you're not bounded, you can't add up those areas. So if it goes on forever in one direction,
Infinitely large.
right, you can't do it. So you have to have that. Here we have an asymptote going to infinity. We're not bounded in any way, shape, or form. Therefore, that area cannot exist. Or it does exist, but you can't find it using the methods that we use. There could be something else. I'm not sure if they have a way to do that, to be honest with you right now. But I, for what we know, that doesn't work. It's not -2. If you think about 1 over x squared, that's positive anyway, isn't it?
Yep.
And if I did my signs wrong, it would come out to 0. I don't think I did I do my signs wrong?
No.
Hope not, I did it real quick. But if you did, it would just come out to 0 anyway, which you know there's an area. It goes like this. It's a positive area, so that it makes nonsense. And it's because there's a domain issue. You had it right. It's not the negative. It's the fact that we start here, we end there, and there's a problem between them. That would be the problem. Do you get it? There's a problem at 0. 0 is between -1 and 1. You have to be at least bounded between there. Typically, you have to be continuous and bounded, and that would make it work. Yeah.
even if our bounds were a little bit wider, it still would be undefined since that you can't measure at x equals 0.
What I mean by bounded isn't this way. I mean this way. You have to have this.
Upper limit.
Here's a curve between these 2 points. It's got to have a low point and a high point, which means you can come up with something here and something there that's between. Actually, really, it's just, if you're just talking about the x-axis is only above, it just has to be bounded above, it doesn't go anywhere. If it was below the x-axis, it'd be bounded below. So this one's really irrelevant when you're talking about the x-axis. That one doesn't matter. But if you find an area here, it's got to at least be bounded above. When you do something like this, hopefully you see the problem. Do you see the problem? How are you supposed to add that area up? That goes to infinity. You can't do that. It doesn't. I don't know what the area is. I don't know if you can. If you can say infinite area, I would assume so because it's going to infinity. But you can't calculate it like this, How many people understood that? Where the problem is? What's the problem again? Explain it to me again. What's the problem? Domain issue. Why a domain issue? Someone else. Domain issue. Why?
Because it's undefined.
Where?
At 0.
At 0. And why is 0 important?
It's in our.
Because it's within
Aha,
constraints.
aha. It's actually in our interval. If I had done this, would there be a problem?
No.
Not at all. No. But if I cross over that undefined point where we have a domain issue and going to infinity, that's an issue for us. We can't do that. Now, is it kind of clear for you? All right. You guys had it. Come on, you should have known that. You should have right at the bat. You should know that this picture looks like this, too. Like that. Just by thinking about asymptotes, you should know that. Asymptote going to infinity is like this, asymptote in the middle goes like this, sign analysis says they're both positive, plugging in positive is positive, plugging in negative is positive. It goes like that. You should know that. Anyway, this, none of that works.
So we just put undefined for,
Well, this one you would do.
oh yeah, the new one we would do, but the original problem would just write undefined or.
You would explain to me that there's a domain issue and that since our bounds are going from -1 and cross over somewhere where we have a vertical asymptote, therefore in no way can find the area of that curve between those 2 points. Okay, now let me show you one more thing that we can do. Are you ready for it? Were there any more questions on that one? That's a good one, huh? Even though, because it looks like you can do it, and you do it, and you go, I win, -2. But you don't think about what the function actually is, it burns you up. You don't want to do that. By the way, don't assume that all of them are going to be like that on the test. So if all of you go, oh yeah, it's got a domain issue, I can't do it, you're probably mistaken. I'm not going to give you 20 integrals that you can't do, okay?
You might get one of those 20 right.
Yeah, maybe one, maybe one.
Wishful thinking.
I always find that funny. I tell you one thing and then you always assume it's that thing. Oops. Oh, you know what? I could show you one more thing on this so that you would actually see it as well. If you should know, going back up here, you should know that because of our property that we had, that should be true, right? Shouldn't it? And now when you think of that, you go, oh, there's a problem there. You see the problem there? Now it's 0, the ending bounds there. You couldn't even, if you tried to do the integral there, you couldn't even plug it in. You'd have undefined and undefined, and that would show it to you right there. Okay, so it's tricksome when I put it like this, but when you see it like that, you go, oh yeah, that's more clear. That's more. Now, how about this one? Oh my gosh, a piecewise function. Can you do it with a piecewise function? Of course you can. It's actually not even that hard. What you have to do, though, is realize what this question is asking you. This question says, I want the integral from 0 to 6 of f of x, where f of x is defined as x cubed when x is bigger than or less than 2. 5x minus 1 when x is bigger than or equal to 2. So, can you break up this integral in a very similar way I did up here so that you can make maybe 2 different integrals? Well, let's do that. Where's our first integral going to start? Let's do this. 0, very good. And where's it go?
2.
Yeah, because that's our separating point over there, 2. What function is defined between 0 and 2, the top one or the bottom one? Good, the x cubed, very good. Plus, because we know, using the property I actually defined up here again for you, we can separate an integral into 2 different integrals by matching up the bounds. 0 to 2 and then 2 to 6. Of which other?
5x minus 1.
If some people might have a question, well, does it matter that this one's actually less than 2 and this one's greater than or equal to 2? No, not really. We have such small rectangles, it doesn't really matter. They're all going to mash together anyway, so no, not really.
If you had, say that it wasn't greater than or equal to 2, then it would say it was just greater than, it would matter, correct? Because then you'd have a gap right there.
No, it'd still do it. Although, wait, did you say that this one changed?
No, the one below it,
Oh,
say that equal.
that didn't have it?
When
Then
it-
you'd have an undefined
Defined
point.
point.
Yeah, I'll say it this way, the area of one point doesn't even exist anyway. So you could technically do it with 2 different integrals because the area of that one point doesn't matter. It's 1 point. The width of 1 point is, you can't do it. There is no width between 1 point. It's a point is that which has no breadth, which means it does not have a width. No matter what the height is, the area would be 0 of that single point. However, this wouldn't make sense from 0 to 6. This one couldn't be given to you like that because this says continuously from 0 to 6. And so that really wouldn't make sense. Does that make sense? I couldn't do that to you, because you wouldn't have the ability to break it up, because to break it up, it does have to be continuous. I think I gave that to you. I don't know if I stated it word for word the way the book does, but in order for that property to work, the ability to split up the integral, it's got to be continuous. That's another reason why this one would fail. That's not continuous. Do you get that? So you couldn't even split up to begin with. It's got to be there. It's got to all be there. You got to have the ability to break it up. That's the only way this works. Otherwise, you are missing points, like you pointed out. That's a good point. Great question. I talked through that pretty quickly. Are there any questions about what I just said? Were you able to follow it? Yes.
So, same thing if the bottom function was 5x minus 2 or something, and there was a jump, then you wouldn't be able to do it either? Or,
If they didn't actually match, oh, that's a good question. You mean if there's an actual gap, like if we plug in 2 and it doesn't,
right, like they're not the same for both functions?
yeah, they're not in this case.
Oh, you're right, they're not.
Yeah, they're not in that case. No, it doesn't matter, just it means that you're defined for every point from, in this case, from 0 to 6, that you have something for every one of those points.
Okay.
That's the ability to break that up. Now, in practicality, does that, if you add those areas, or you add, what was it here? If you add those areas, it's going to be the same. You just can't do this if you don't have that. That's the point. Does that make sense? You just can't do it. Legally speaking, you can't do it.
Theoretically, it would make no difference, so.
Theoretically, it does make a difference, that you cannot
practicality,
actually do
yeah.
it. Practically, this area plus this area will equal this area. Yes. Sorry.
Right, now.
This area plus this area plus this area, I should do it this way. This area plus this area, even like that, will equal that area because the area under a point is 0, but you can't do this unless you have this. That's the point. Dang, good questions. You're making me work for my money today. That's why they pay me the big bucks, you know that, right? Explain all this junk to you. I don't get paid big bucks. The Audi I drive is 01, so. Hey, the integrals aren't actually that hard. It's plugging the numbers and getting that right, huh? That's the biggest problem in math, is the small stuff. My gosh, don't forget any signs, don't lose anything. Keep track of all your numbers, get that stuff right.
Why is that X?
Oh, 4, sorry.
That was, yeah.
New math.
It's government policy.
Did y'all get your integrals correct? You got x to the 4th over 4 from 0 to 2. You got 5x squared over 2 minus x. You didn't forget about that minus 1, right? From 2 to 6. Did you get that far? Okay. Now we plug the numbers in. I don't know if I should count on you guys on that one.
Just give us some more trade, we'll get that.
Right. You know, you really need some brackets and parentheses on this thing, because you got stuff going on all over the place, especially when you have those multiple terms being added or subtracted. This one's pretty easy. This one you just plug in the 2 and you plug in the 0, and that's very straightforward. You get 2 to the 4th over 4 minus 0 over 4. This next one, you got some things going on. Notice how you have to plug in the 6. That's giving you the 5 times 6 squared over 2 minus 6. Then you plug in the 2, but you're subtracting. Remember, it's f of b minus f of a. The whole thing. Do you see why the parentheses are important here? Okay. If you wanted to distribute, you distribute, and that sign would change. Now, typically, order operations say you add all that up together before you subtract anyway, but it's important that you know that. So we're plugging in the 2. We got all that down. You want to help me with the math? That should be what, 4?
Yeah.
4 plus, so that's 4.
84.
36,
It's 90.
90,
90 minus 6, 84.
84. Okay, so that's 84. Eight minus 8, right? Looking like 80 to me. Did you get 80? Cool. How many people were able to find the 80? Did you feel okay with it if you weren't able to actually do it on your own? You were okay with it? Now, what's it represent? What did we just find? The area of what? Yeah, of this, when it's defined this way between 0 and 6, you found the area under that curve. Or actually, the area, the net signed area. If this thing went below the x-axis, I can't see that it does, but if it did go below the x-axis, then we would actually have the area that takes the difference between the area above and the area below. That would be net signed area. Do you feel okay with this example? Do you have any other questions?
So whenever we have multiple terms in one, we just take the first one, put in for all the x's, solve, and then take the bottom
Absolutely.
one.
What this says to do is, you plug in the 6 the whole way through, you figure it out. That's the area from 0 to 6
Right.
of this function. Then you subtract from 0 to 2, and that's what that's going to give you.
And so no matter how many terms we would have.
Plug them all in, then subtract, and then plug them all in. And that's what you do. You got to plug them into everything. Yeah, and for this instance, your x becomes 6 everywhere you see x. For this instance, your x becomes 2 wherever you see x, and then you subtract, and that's what this meant. F of b minus f of a. That's what that meant. You take your b, you plug it in. You take your a, you plug it in, then you subtract it. Now, what we've been talking about this entire time is something called net signed area. I gave you net signed area before. What net signed area was this. You took the area 1, you took the area 3 because it was above the x-axis, and you subtracted area 2 because it was below. That is what your definite integral will do automatically. Without asking you, it will do that. Why does it do that? Well, because the area below counts as negative area for a definite integral. That's actually one of the things that we saw with our switching of signs. That's another reason why that comes out negative, is because when you go from whatever this point to whatever this point is, if it's below, it's going to be subtracting those areas and thereby causing them to be negative. So this counts against your total area. Now, in order to count total area, what you do is this. You say, I want to count up the area that's between the two curves. I don't care which one's on top or which one's on bottom. I want to find out the actual area between them. So find the area that's here and here and here. That would be total area. This is net signed area. So one question I have for you is, how in the world could we get this area to become positive? How would you do that?
Absolute value.
Say it louder.
Absolute value.
Absolute value will absolutely take any negative thing and make it positive whenever you see it. Right? So what we're going to try to do is this. We're going to try to take this one and flip it over and say, all right, well, total area then should become area 1, area 3, not that. We don't want that. That's going to count as negative area. What we want to do is find a way to flip it over here and make it count for us. That would be total area.
Would you just flip this?
For total area, we need to change the sign of area 2. In other words, if you kind of go on further than this, you say, well, I want to change the sign of any area that's below the x-axis. If I can do that, then that negative area actually counts as positive area, and we add it up together. And what we end up doing is we end up finding the area between two curves. One of the curves is the function, the other curve is simply the x-axis. Now, in section 5.1, we go further, and we actually do legit two curves, not just the x-axis. But keep in mind that this is exactly what we are doing, is finding the area between two curves. So I'm going to draw on this later. You understand? So this is one curve. This is the other curve. It's a very simple curve. It's just x equals 0. But what we're doing is finding the area that's bounded between two curves. That's what we're doing literally. In order to do that, that's positive, that's negative. We have to change the sign of that for the x-axis. That's the idea. So for total area, we need to change the sign of area too. Or in other words, the area of any piece of the region that is negative. In this context, excuse me, that's the area that's below the x-axis.
Are we saying we want FOB plus FOB?
No, I'll show you how to do it right now.
Oh.
Okay, now check it out. Here is net signed area. Net signed area said you start at A, you go to B. You just take the integral of whatever function you have, and whatever happens, happens. Positive area means most of it's above the x-axis. Negative area means most of it's below the x-axis. Even if we cross over, it just basically says your net change, what is mostly happening, whether you have more positive than negative or more negative than positive, no matter what it actually is on your graph. Does that make sense to you? Now, total area says, no. We're going to take all the negatives and we're going to make them positives. What are we going to do with the positives? We're going to leave them alone. The thing that leaves positives alone and changes negatives to positives is, of course, absolute value, like you said. So total area says, all right, we're still going from A to B, but now we have the absolute value of f of x. Just remember one thing. The absolute value of f of x, or the absolute value of any function, is actually piecewise. So it's going to look kind of like this, is why we did this first. It says you keep f of x if f of x is positive. You make it negative f of x if f of x is negative. That's the way you do absolute value. It says, shoot, man. If your function's positive, why are you going to change it? That's going to be a positive area. In fact, we know it's going to be a positive area from one of the properties I taught you before. Whenever your function is completely above the x-axis, hopefully you're listening to this, whenever your function is completely above the x-axis, your area would be positive. You remember that? Whenever your function is completely below the x-axis, your area would be negative. If we make an area, a negative area, negative, that's changing the sign of your negative area, it will become positive. So here's what it says. This area will be positive. This area will be negative, so we're going to change the sign, thereby making it positive. Are you clear on this? Did that blow your mind? Like a grenade? Did I really? Sweet, I hope so. Would you like to see an example in practice?
Yeah.
It's not hard. Not hard. It's going to look a lot like this, as a matter of fact. There's just one more step to be able to figure out where you separate it. You see, we just did this piecewise function, only in this piecewise function, I gave you the separating mark, right? I said you go from 0 to 2 and 2 to 6. All you're going to have to do is figure out where that mark is for yourself. What that's called is a sign analysis test. Bam! Told you this is exciting. Exciting stuff here, folks. Sign analysis. How can you not get excited with sign analysis test? Find the area between f of x equals 1 minus x squared and the x-axis on 0, 2. Well, what we mean is total area. Let me insert that right here. Find total area. Total area between them. Because net signed area would be very easy. Net signed area, you would just take the integral. Look at, here would be net signed area. It would be from, where would your integral start, ladies and gentlemen? Where? Where would it end? Your function is?
1 minus x squared dx.
This right here is net signed area. Do you understand? It would take the area above the x-axis, subtract the area below the x-axis because it would be negative, and that would be your net gain, your net change in area. Okay, that's what that would be. This says, no, total area. The total area will do this. It will take the negative area, it will flip it above the x-axis, or at least it will change the sign of it, and that would count as positive area. It would say, I want to find the area between them, take all of it and add it all together. No matter what the sign is, add it together, because the absolute value will change it to a positive. You following that? Okay, so how do we actually do it? Well, here's your steps. Step 1. You got to set your function equal to 0. Do you know why you got to set your function equal to 0?
Y-intercepts.
Not y-intercepts.
X-intercepts.
Hey, if you're trying to figure out where the function is above and below the x-axis, you better find out where it crosses the x-axis. That makes sense to me. Does that make sense to you?
Yes.
If you know where it crosses the x-axis, then you can perform a sign analysis test, plug in some numbers easily and say, oh, it's above, it's below, therefore I know when the area is going to be positive, when it's going to be negative. You get me? Okay. So set the function equal to 0 and solve. So for us, I'll do that in purple so you see the work over here. We're just going to get 1 minus x squared equals 0. Well, there's only like 2 more steps. What are you going to do with this?
X squared.
Probably add x squared, yeah. And then you're going to,
Square root. You get plus or minus
yeah, sure, square root plus or minus x equals negative 1 and 1. Raise your hand if you feel okay with this so far. Okay, now the next step. You got to set this up correctly. What you're going to do is you're going to do a sign analysis test. Sign analysis. But you only need a few of these points. What points do you need? Well, let's see. Do you need the 0? Yeah. Do you need the 2? Of course. Do you need the 1? Yes. Do you need the negative 1?
No,
No, you don't need that one. Why not?
it's not within the constraints.
Doesn't care. So really, you're going to make a sign analysis with your endpoints of your interval, your bounds of integration, and whatever points fall between them. That's it. So make it with your endpoints and your x-intercept that fall within those endpoints.
No, see, if you have no points of intersection within your bound, you just use your 2 endpoints.
Then you know what? You won't even need that. Because it's either all going to be positive or all going to be
So
negative.
you just test one and go with it.
Yeah. So sign analysis with endpoints and any x-intercepts that happen to be within your bounds of integration. Well, let's go ahead and do that now. So we're going to make a sign analysis test. Here's how sign analysis tests look in case you forgot. What you do is you take your bounds of integration first. The bounds of integration start at 0 and they end at 2. You take any of those x-intercepts that you had. Those are the places where you're crossing the x-axis, and therefore that's the places where your signs could possibly change. Well, only one of them. That's 1. Feel okay with your sign analysis so far? After that, after you make that number line, you just determine when f of x is above 0 and f of x is below 0. That's just plugging in a point. Plug in 1 point for each of these intervals. That's only 2. You don't have to go over here. I don't care. I don't care about that one either. I care about these 2 intervals. Plug in 1 point, see whether it's above or below the x-axis. recall that if it's above the x-axis, the area has to be positive. If it's below the x-axis, the area will be negative. And this is the separating point between those two areas. That's why we set it equal to 0. So we're going to determine when f of x is greater than 0. That would be above the x-axis. Or less than 0, below the x-axis. Have you done it already? You plug in probably 1/2. Where are we plugging this in, by the way?
To our original function.
Yeah, plug in the function. It's going to tell you, I don't care about the number, I care about the sign of the number. Which one's 1/2?
Positive.
Okay, so this is positive and this one's negative? Cool. What this says is that from 0 to 1, I'm above the x-axis. From 1 to 2, I'm below the x-axis. We're going to have to come up with that sign change. We're going to do it right now. What we do is we're going to split up the integral using the definition for absolute value. Okay, here we go. This is the good part. Let's find total area. So where are we going to start and where are we going to stop for our first integral? Where are we going to start?
0 to 1.
0 to where?
1.
Cool. Yeah, absolutely. Now, think back to this. What the absolute value of x says, absolute value of f of x says is, if it's positive, you leave it alone. If it's negative, you change the sign. So when this is positive, here's what we're going to do. Between 0 and 1, do I change the sign or not? What do you think? I'm going to leave it alone. I'm just going to do 1 minus x squared. Why don't we have the absolute value still? Absolutely not. I'm actually using the definition of absolute value. Right?
I bet you're,
Because you
you
don't
don't
need it.
the
Because the value of that,
you're not changing the sign.
I'm actually using this to change it. I'm saying, well, if f of x is positive for that region, then I know the absolute value of f of x is simply f of x. I know that this is positive for this region, therefore the absolute value of f of x is simply f of x. That is what this says. It says, hey, if it's positive, you don't change anything about it. You basically just drop your absolute value signs. Are you with me on that? Okay, dx plus, again, the reason why we do this, just like the piecewise example, do you recall that between 0 and 2, if I find some intermediate point, I can split up my integral from 0 to 1, and then also from 1 to 2. You remember that? It's continuous, no problems, no breaks. That's great. Between 0 and 2, we're going to go 0 to 1. We're going to go 1 to 2. Now, between 1 to 2, this is why we did our sign analysis test, our function is negative, which says it's below the x-axis. It says that the absolute value of x, well, if f of x is negative, you're going to have to change that sign. You follow? You can't just drop the absolute value because it's not positive. You go, all right, well, back up here, I'm going to have 1 minus x squared, sure, but negative. If it makes you feel better, I can do this too.
They can distribute maybe.
You can do lots of things as you want. Show of hands, how many of you feel okay with that so far? Okay, I'm not going to do much of a recap. I'm just going to say what we're doing here is basically using a sign analysis to our advantage to determine when our function is positive and negative. Where it is positive for that region, you leave it alone. You just write it, no absolute value. Where it's negative, you just write it, but you have the negative in front of it. This is the reason why, though, is because we have this scenario, because we know if the function's above the x-axis, the area will be positive. If the function's below the x-axis, it will be negative. And that one nice property that said if you have a continuous function between 2 points, you can split up that integral into 2 different integrals by using some number that's between them. That's all these properties coming together. There's a lot of properties we're actually using here to be able to do this. It's kind of cool. Now, what I would do with this integral, I wouldn't distribute this, I'd pull the negative out. I'd just pull the negative out, just make it a minus. That means that the area is 0 to 1 of 1 minus x squared dx minus 1 to 2, 1 minus x squared dx. I'm doing this just so you can see this part of it. Check it out. Look. You know this area is positive, right? Right? You know this area is going to be negative, right? Minus the negative area, that's adding the area. That's all this really does for you. Why don't you go ahead and do those? See what you get. Did you get 2? I got 2. I don't know if I did it right. I did it pretty quick. Did you get 2? If you didn't get 2, it's all fraction work, but hopefully you got 2. How many people were able to make it down to this part right there, that part, the integral? Did you get that far? Good. Did you plug in all the numbers at least this far?
Yeah.
From here on out, it's just fraction work. Calculators are fine. I don't care. As long as you're able to get the right answer down here, be able to do that. Can someone please double check my work to make sure that I am correct on that?
Yeah.
Make sure all my signs are right. You did? How many double checks do I have that got 2? Good for you. Good for me, actually. I did it. Shoot. Come on. All right, well, we're ready to tackle the fundamental theorem of calculus part 1. The first part we did was actually part 2. That was all the area things and being able to calculate a definite integral, which means an area, by doing that whole subtraction. Find the antiderivative, plug in b, find the antiderivative, plug in a, and subtract the 2. That's the fundamental theorem of calculus part 2. The part 1 basically says this. It says that derivatives and integrals are inverses. It says one undoes the other. That's basically the idea in the most common, small sense I can make it. So let's suppose we have this function, y equals f of x, is some function, and it's continuous over a certain interval. Starts at a point, and ends wherever we want. Ends at some x down the way. You get me on that? Some x, even changeables, provided it's continuous up to that point. Then the area is a of x. We already know that. Area is going to be some area function such that when I take the first derivative of my area, what does it have to give me in this case? Say it again. Very good. So if f of x is continuous over this, then the area is a of x, some area function, and the derivative of the area function must give me back my function, my original function. That was the antiderivative thing, saying that this is the antiderivative of that, treating this like a derivative from going backwards. Well, I could write that a different way. I could write that also as the area then should be the integral of f of x. We also had that from what we've been studying, right? It says that if I want to find the area, it should be the integral of f of x dx from a to x. You okay with that as well? It says that the first derivative of the area is going to give me my function back. Therefore, the antiderivative of my function between my two bounds, whatever they happen to be, should give me my actual area. It should give me the area. Now, this is in terms of not a b, but an x, so as to give me the a of x, not the actual area. Does that make sense? It'll be a function of the area. That's what it's saying there. How many will feel okay with that so far? Now, I'm going to do one thing so that we don't get a little bit confused, because it's kind of awkward to have a function in terms of x and then have a bound of x. What we use here is called a dummy variable. It really doesn't matter. It's just a variable that we're going to be integrating because you're going to be plugging in x later anyway. So the x's will appear. So typically what people do at this point, they go, you know what, let's not call it f of x. Let's call it f of t dt. They make it a dummy variable. Now, why the dummy variable doesn't matter is because when you think about it, when you take the integral of this, you're going to have a function in terms of t, correct? But look at your bounds of integration. You're going to go from a to x. You'll be plugging in the x's somewhere for your t's. You'll reinsert them into your equation. That would give you an area function in terms of x like we're looking for. How many people feel okay with this so far? Okay. Well, here's the basic idea. I'm going to try to tie all this together for you real nice and neat. I'm going to try. I really will try here to make it neat. Would you agree that this equals this? Yes?
Mm-hmm.
For sure. You believe that?
Yeah.
Oh, then we're almost done. That's fantastic. Very good. Because this means a derivative, right? That means a derivative. So the first derivative equals f of x. The first derivative equals f of x. However, we also have this statement right here. What I'm going to do is make a little substitution right there. So what this says is the derivative of a of x here's another interpretation of a of x. What's it have to equal? What did this equal? Are you seeing that this is the same thing as this? Yes or no? This is a of x, so is that, from right here. I just went this way. I made a of x that way. That has to equal f of x as well. This right here is the fundamental theorem of calculus part 1. Yeah, because we talked about this first.
And so where you have the f of t, because of the way you do the integral, you're just swapping it out and reinserting your x to make it come out with f of x, not f of t.
Right. We use the t here so you don't get confused in x with x, because it's hard to think about, oh, I'm going to plug an x in for an x, that's weird, why do we do that? But so what we do is we use a t and say I'm plugging in both x and a for my t.
Or you could like use x subscript 1, x subscript 2 to keep them separated. Or it doesn't matter what we use besides t.
No, you could use h there if you really want. T's a dummy variable, it doesn't really matter. You're gonna be integrating some variables, right? For those variables, you'll be plugging in x's. That's the idea. Did you follow? A of x equals this. Derivative of a of x equals this. Therefore, derivative of this equals f of x. That's the thing about theorem of calculus part 1. Here's what it says in plain English. It says, if you take a, what's this stand for? What's this stand for?
Integral.
It will give you back your,
Function.
that's it. If you take a derivative of an integral, basically it undoes everything. It essentially says they're inverses. It says a derivative undoes an integral. An integral of your function gives you something, right? An area function, as it were. Then you take a derivative of that, gives you it right back. Gives you your original function back. Now, why? Why is this important? Because that seems pretty common sense, doesn't it? I mean, we've already kind of thought that, well, I mean, shoot, if an integral is undoing a derivative, it should be the inverse of a derivative. This proves it, that a derivative is an inverse of an integral. But why we do it is because sometimes it makes certain integrals very easy to do. Here's why. Maybe not certain integrals, but certain computations very easy to do. Without doing any work, you can tell me what this is, actually. Say what?
T to the fourth.
Not t to the fourth,
X to
you're
the
very
fourth.
close. X to the fourth, without doing any work. Why? Well, because you have a derivative of an integral. The integral starts, I don't care, but it ends at x wherever it is. That means that this is going to be whatever our dummy variable is, but with an x instead. So this becomes x to the fourth. By this theorem. By that theorem. If you want to see it proved out, which we can do that directly, I'll show it to you right now. That would be a derivative of, if you did the integral, you're going to get t to the 5th over 5 from 1 to x. True? What that would give you is a derivative of x to the 5th over 5 minus 1 to the 5th over 5. Do you see where the x is coming in? Do you see why we have a dummy variable? It doesn't really matter. You're plugging in x for it anyway. Okay. Do you see why this number doesn't matter? When you plug in a number to that, you're going to get all constants. What happens when you take a derivative of constants? 0. So really only that matters. So you're going to get a derivative x to the 5th over 5 minus 1/5. What's the derivative of x to the 5th over 5 minus 1/5, ladies and gentlemen? Which proves it. Well, at least for this example. I basically kind of proved it here with this statement here. It's done. There's some more serious proof to it if you really want, but that's basic enough for us. Now, that you could do directly. Some of them you can't. So when you get to this integral like this, I don't want you to spend too much time on it, because there's no way you can do this integral in this particular class. Let's say you had something from 1 to x sine of t over t, dt. You can't do that integral directly. You can't do it the same way I did it, all right? It's not, you can't just hammer at it. Not in your integration table, you can't do it. However, because you have a derivative of an integral from 1 to x, from any a, to x, you can use the same property right here. So how much is this going to be equal to? Sine x over x is right. That's exactly correct. Now, one thing, it does have to be defined for the entire, just like, remember how we found out last time, it's got to be defined. You can't, it's got to be continuous. It's got to be very nice. You can't have the undefined points. It has to be bound somewhere. Are we okay here? 1 to x. Remember, this is the small number, so it can't go backwards. Are we okay? What's the one number that's not okay? We miss a 0, so we're okay. If this had gone from like -1 to x, we'd probably have a problem because we couldn't evaluate that integral. Yeah, that's it. So when you get to some of your homework, some of it's going to be kind of easy. If it looks like this, a derivative of an integral, and you're going from a to x, and it's defined for that whole region, I mean, it starts higher than any problems that you have, that's all you got to do. Plug in your x's and you're done. A derivative will undo an integral. That's the fundamental theorem of calculus part 2.
Part 1.
Part 1. What did I say?
2.
Part 1. That's it. Oh, people understood that. Good for you. That's fantastic.
I wish all integrals were like that.
I know, right? Well, the thing is, we don't always take derivatives of integrals right next to each other. It doesn't happen very often, but it's a statement that says it is true. It's proving that they are inverses. Now, we're going to move on. This is typically a different section in most other books, but this book ties it all together with this. We're going to continue doing definite integrals, only we're going to do some more, I guess, tricky ones. They're not super tricky, but they're going to incorporate something you've already learned in this class, which I guess is kind of nice, but we haven't dealt with it yet. We're going to start talking about how to do definite integrals that might involve a substitution. You ready to learn how to do that? It's not hard. You've already learned substitution, right?
Yes.
So if you've already learned substitution, I just have to tell you what to do with the bounds of integration. After that, everything falls into place. So same idea. Let's look at how we deal with bounds. That'll be the rest of our lesson. Okay, so, what are we on? We're still on 4.5. This is still an extension of that. So we'll talk about definite integrals. But this time we might have some substitution. It's still in your best interest on your homework to check if you can do the integral without substitution. If it's just a simple distribution or a simple changing of some exponents from square roots into 1/2, I think we had one of those last time, right? And you combine them, that's probably easier than substitution because substitution might even work in that case. But if you have to use a substitution, at least you know how to do it already. There's basically 2 methods. I'll show you method 1 first, and I'll show you method 2. Method 1 says this. It says you're not going to change your bounds. You're going to do the same exact thing as before, but you're going to be sure to substitute back in for u before you evaluate. So method number 1 is don't change bounds, sub in for u at the end. Don't change the bounds. Substitute back in for u before you evaluate. And you'll see exactly what I mean on this example. There you go. Okay, let's look at the integral. This is the first time we've had like a, honest to goodness, integral with some numbers up there and something that wasn't just super, super basic. So this looks like a real integral with some real numbers and some honest work to do. First thing, could you distribute everything out? You could. You really could in this example. You probably wouldn't want to though, because that's a power 3. It's going to take you a long time. So substitution in this case would probably be your best bet. Ignore the bounds when you're picking your substitution. It's just a basic integral, just like you did with indefinite integrals. Pick the correct substitution. Why don't you do that now? At this point, I'm hoping that most of the substitutions are pretty obvious. The only times they maybe wouldn't be is with some of the square roots. Sometimes people forget about that. Or with trig functions. Sometimes they're not obvious. You have to guess and check. So, u, what's u?
X squared minus 1.
Good. What's du?
Yeah.
Don't forget the dx. You need the dx. And then how I've taught you how to do this is I've had you solve for dx. That makes the substitution nice and neat. So solve for dx, you're going to get du over 2x equals dx. You okay with this so far? Everybody? Okay. Now what do we do?
7.
So we're going to have, what are we going to have? Why don't you tell me exactly?
4x
Okay, I heard 4x. What'd you say after that?
u
Perfect. And then what?
and then du over 2x
Excellent.
from 2 to 0.
So we're going to talk about that in a second. Firstly, how many people feel okay with our substitution? 4x is still there for right now. The u cubed comes from u cubed dx. No, not dx anymore. Du over 2x. And then we start simplifying things. And then Michael said something interesting from 0 to 2. Yes and kind of no. Yes and no. We're going to put it there. But I want to show you why method 2 can do something different for you. Because as soon as you do this, from 0 to 2, as soon as you do that from 0 to 2, look what's going to happen. Sure, you're going to eliminate this 2, and that's going to become a 2, yeah? And you're going to eliminate this x and this x. And what you would get is 0 to 2 with a 2 out in front of it. Do you see where the 2 out in front of it's coming from? That 2 pull out front. U cubed du. Which variable? What's your variable? U. Yes, it's u. Not you. U. It's u. What were these bounds originally in? So we kind of have bounds that don't match our integral right now, which is sometimes leads to problems because what people do often is they'll do this. They'll go, okay, hey, I know how to take an integral. It's very easy. I'm going to have 2u to the 4th over 4, and then they do this. Explain to me why that might be incorrect.
You got it in terms of x.
You haven't tested it.
Right. These are in terms of x, right? But the integral makes it seem like you're plugging them in for u. Now, you can do it this way. You can. You really can. Provided that you do one thing. Provided that you don't change the bounds. We didn't change the bounds. And substitute back in for u before evaluating. So not here. This would be the wrong way to go. Do you see why it's the wrong way to go? Honestly, do you see it? You're trying to plug in x's for u's. That's not going to happen. So instead, we're going to do a little bit of simplification still. We're going to get u to the 4th over 2, and you all said that you're going to substitute back in for u in terms of x before you plug this in. You see, if these are in terms of x, I want my function to be in terms of x, my integral to be in terms of x, what I got to be in terms of x before I evaluate. So we'll substitute back in for the u. We'll get our x to the 2nd minus 1 all to the 4th power, then over 2, and at this point, this is where I should evaluate. So right here, let's look a little bit cramped up there. Now we get to go from 0 to 2. That's okay. That says, now that we have this in terms of x, great. They match up with our x bounds that we started with. Now plug in the 2, plug in the 0. Why don't you do that and see what you get? Don't neglect that 0. 0 squared minus 1 isn't 0, so you're going to get something over there. I got that. Did you get that?
Mm-hmm.
Cool. What's it mean?
There.
It's an area. What type of an area is it? Total area or net signed area?
That's
Good, we haven't talked about absolute value or anything. Not sure if that one's going to have any negative area. If you graphed on a graphing calculator, you could tell. Or if you wanted to find out total area, what you would have to do is find out whether that's above or below the x-axis for all of those points. I'm not sure in either case. Maybe you can look at that. But you'd have the absolute value for total area. You remember doing that from last time? The absolute value, you take this, you set equal to 0, you'd have your endpoints and any points in between there that would change the sign of that thing, and you separate those two intervals, and that's how you do that problem. So this actually is net signed area, whether or not we have it all above or below. And this, if it was all above the x-axis, net signed area would be total area. But if there's any area below the x-axis, it would have automatically subtracted in there for us. So that's the case. By the way, has anyone graphed that? Do you know if there is any area below the x-axis between 0 and 2? I guess we could find out real quick.
That whole function. Between 0 and 2, yes, there is negative. Yeah, there is. Between 0 and 1, it looks like.
This is negative?
Yeah.
Okay.
So it looks like, I mean, there's a little portion of
Like that?
just a little bit on the side of 0, it looks like, well.
Aha. See? You can see. Yeah, we have a little bit below the x-axis between 0 and 2, so that's going to be counted against our area right here. So this is actually total, not total area, this is net signed area. It's discounting the part between 0 and 1, and then we have from 1 to 2 that would actually be positive, but it's greater than the negative area. That's why we have a positive 40 out of that. How many people feel okay with that so far? All right, cool. Would it be substantially harder to do that? Substantially harder to break them up? Not really. It's actually just a matter of separating our integral, going from 0 to 1, and having the negative in front of that, and then going from 1 to 2, and doing it just like we just did. You just plug in some different numbers. So it's not that much harder, just you have to do the integral twice. So I don't want to do that right here because we have to change bounds a lot in the next example, but that would be something to talk about. Are you okay with this first example? Do you understand the idea of not changing bounds? Basically the same exact thing you do for every example. You just don't change the bounds, you do the integral like you normally would, change it back into x like you normally would, and then plug the numbers in. That's the first method. Second method says, well, maybe not necessarily a quicker way. It's not quicker. Maybe we can just do it a different way. In either way, notice that you're going to be plugging these numbers in. You will be plugging in 0, and you will be plugging in 2. You should do it at a different time. So we're going to talk about method 2. I'll show you how that works.
Do you have a preference on which method?
I'll tell you which method to use on the test when I want you to use it. If I don't tell you a method, you do whatever method you want. Okay?
So we should learn both methods.
You must learn both methods. Yeah. Okay, method 2. Method 2 is you change bounds. You change bounds during your first substitution. If that's the case, here's what I'll give you like a little foreshadowing of what's going to happen. You're going to change your bounds from x's into terms of u using your substitution. If you change your bounds into terms of u, do you need to substitute back in at this point for x? No, because they'll be in terms of u. So if you do method 2, you change your bounds, and then you do not substitute back in before evaluation.
It's the same.
Tell you what, let's do the same example. Can we do the same example? Just do it a different way. So you can see I'm not full of smoke here. It really does work out. I'm not here to reteach you how to do substitution. I've already taught you everything you need to know. Doesn't change, so that's nice. You'll still use the same substitutions no matter what. What I'm here to tell you is there's just a slightly different way to do it. So if we pick the same substitution u is still x squared minus 1, and hey, du is still 2x dx, and sure enough, du over 2x is still going to equal dx. That doesn't change at all. You still okay with that? Here's the change. The change says, well, since we're substituting everything anyway, I mean, we're substituting this for u, this x part for u, and this x part for u, why not just do the bounds as well? Why don't we substitute those things for u as well? And here's how to do it. All right, well, that's a good idea, Mr. Leonard. Let's try. Well, here's the point. When you look at that, that says x is going to become 2. That says x is going to become 0. Why don't you find out what u would be when x becomes 2 and u becomes 0? And that's the question. Notice how we're actually doing that right here. We're plugging in 2, 2. We're plugging in 0, 0. It's just within the evaluation process. Here you just do it beforehand, so that when you get your bounds, it's in terms of u, so you don't have to do this step. You just go directly from here. It's basically, do you want to do the work beforehand, or do you want to do the work after? Doesn't matter, you're going to do the work either way. So it's really up to you. Now I'm going to make you learn both. I'm going to tell you what to do, but it's an option for you. You got it? Okay. So we'll say if x equals 2 and if x equals 0, this is the whole process of changing bounds. If x equals 2, then u equals 2 squared minus 1. Then u equals 2 squared minus 1. See where the 2 is coming from, right? And u is going to equal what?
3.
Okay. If x equals 0, u equals 0 squared minus 1. Very good. Well, now we can make a substitution with everything, and the bounds will match the variable, which is nice. So let's do it. Do we still have the 4x? Of course. Do we still have x squared minus 1? Of course not. That was our u. Notice how it's going to look exactly the same as the previous problem. du over 2x. The only thing that's going to be different is what? What did the 0 become? What did the 2 become?
3.
It's going to be done the same way. 2 is gone. X is gone. So -1 to 3 will still pull the 2 outside. U to the third du. Hey, we even do the integral the same way. We're going to get 2 u to the 4th over 4. And we'll simplify that. U to the 4th over 2. But now when I do my evaluation, do I have to substitute back in for the u? No, because we did our bounds. And that's the only reason why we had to here, because the bounds were in terms of x. Here you've already changed them. You've taken x's and you made u's out of them. Once you make u's out of them, you can use it right here. Get it? You can use it here. -1 to 3. Because those are in terms of u. Plug them in, you're going to get the same answer. So let's try that. Hopefully you get the same answer. It makes it so your evaluation is just a little bit simpler, by the way, because you typically, because you have this function's gone right now. You don't have to plug that in and then do all the math. Basically, you just do it ahead of time. You're still doing it though. You're still doing it. It's just kind of set aside for you up here, which is, I suppose, nice. Minus negative 1 to the 4th over 2. Well, what that's going to be is 81 over 2 minus 1/2. And again, that's 40. Show of hands, how many people feel okay about both methods? How many people prefer method 1? Method 1. Okay, that's cool. You can. It's fine. How many people prefer method 2? People seem to like that a little bit better for some reason. Simply because you're doing the work ahead of time, you don't have to worry about this later on. The two mistakes I see are this. I see, because the integration is not that bad, I see people making mistakes here. They either forget to substitute back in x here, or they accidentally do it here again, and they get something way off. You see what I'm saying? That's where the mistakes happen. So do one or the other. Now, of course, on a test, I will ask you for both. Maybe not even that one. I'll say do this if you want, but I'll give you some where you have to change bounds. I say I want to see you changing bounds. So you do need to learn that method either way.
So for those intermediate steps though, would you have to use a different notation than method 1? Since like where it says 2 times the integral of u cubed between 0 and 2, that's not actually true, right?
This is slightly off.
Right, so
Yeah.
how would you actually write that if you were?
You'd still write it.
Okay.
You'd lie. Yeah, you'd still write it. But this is one of the reasons why we have that. Because you go, oh, these bounds don't really match up with that letter. Now, you could say, well, maybe we'll just treat it like a dummy variable. It's really not because it's substitution. But we know in our head that we're just going to plug back in for x. So it still works. But those really don't match up all that well. Because actually at all. They're x's and that's a u. Good question. Any other questions before we go on?
So then as a method of checking, if you actually wanted to, you could do both methods and you should.
It has to be the same thing. It is the same thing. You're just doing one part here, and you're doing one part here. One part before evaluation, before even integral, and another part after the integral during evaluation. That's really it. You're doing the same work. Same work. Just two different places. Good questions. Any other questions before we go on?
Why does that work when you change the range of the bounds?
Why does it work?
Yeah,
Well, it's taking a function and make it something else, basically translating,
into a different variable.
yeah. And then you have to change your x variable into your u variable to make it
Oh,
work.
okay.
Okay, so right now this is 0 and 2, but it's regarding the x function. This is negative 1 to 3, but it's regarding the u function that you just created.
Does that mean that the integral that we're translating into isn't within that family of integrals? Is that why it comes out to be the same area?
Oh, that's a good question. You're completely changing the function when you do this.
Right.
You really are. And so you're just making, it's almost magical that it works, kind of cool.
Yeah.
But you're making a different function and saying the areas will be the same because I'm working with different bounds in that function. If you try to do it graphically, I have a hard time believing that 2u cubed is going to look anything like 4x x squared minus 1 to the third. In fact, I know that because a cubic just goes like this, right? 4x x squared minus 1 to the third does, well, we saw it. I showed you the graph. It doesn't look the same. So you're changing functions, but you're only talking about the areas. So basically you're saying the area here between these bounds is the same as the area here between these bounds.
It's kind of like doing a ratio.
I suppose, perhaps, but it's a direct rate. I mean, it's equal. Maybe proportion would be a better way to make an analogy there. But something similar to that idea. It's very cool. Now, you need to know that substitution doesn't always work, right? So you can't always do this. It's only very special cases. I can give you lots of integrals where you can't use a substitution. In fact, most you can't use a substitution. That's special. Every one that you can do a substitution with, the derivative has to be in there somewhere, right? It's got to work that way.
Are we going to deal with the integrals beyond that we can't use substitution for?
Not in this class.
That's next semester.
In your next semester, which I'll be teaching in
Next semester.
fall, no, spring. Spring of 013. A year from now. A year from now. So just go ahead and fail this class or something, take it next semester, pass it with some other teacher, and then come and see me.
Are you going to do 4B and 4C or just 4B?
Just 4B for now.
You need to skip up to 4C.
No. Then my videos wouldn't be in order. See, this wouldn't work. They're going to be in order. All right, what do you say we practice a couple more? Would you like that?
Yes. Oh, yeah, I didn't practice that.
That's stinky enough. Some of you always complain I give you stuff that's too easy in class and doesn't look like your homework. Well, here, deal with that then. Huh? Actually, it kind of does look like your homework most of the time, I would say. Some of them are harder. Would you not say? Didn't say. I think so for the most part. Anyway, that's fairly difficult. Looks like something that would throw some people for a loop. Let's talk about it. Firstly, is it fit your integration table directly, just like that? Oh, not at all. So it's going to probably involve a substitution. If we can do it, it will involve a substitution. Why don't you think through, don't say it out loud, just think about what a proper substitution would be in this case. Think, don't say it out loud. Some of you might be asking, well, could it be 2x? Could it be 2x? If it was 2x, it'd be sine of u to the fifth times cosine of u. Sine of u to the fifth times cosine of u does not fall in your integration table. So that doesn't really help you at all.
Sine 2x and then change it to parentheses to the fifth power.
Okay, let me change it.
And then you'll get to your cosine.
Let me see if I know what you're saying. You're saying that if I change it to this, change it like that?
Mhm.
Okay, that's good. Why is she changing to that? What do you think? It really is easier to see, isn't it? Your u should not be 2x. Not 2x. That's not going to work for you. I know I said it's supposed to be the inside thing. This is an inside thing. However, if you take the 2x, the derivative of 2x is only 2. That's just a constant. It's not going to eliminate the cosine. It's not going to eliminate the sine. You're still going to have sine and cosine. That would be a bad choice. But you'd see that bad choice within like a minute, right? At least I would hope so, because you go through the process, you go, wait a second, something's not right here, Mr. Leonard. I gotta change this thing. And then you change it. Then you look back at your integral and say, well, do I pick sine of 2x or cosine of 2x? Because that's the only other thing I'm going to do. I'm definitely not going to pick to the fifth power. Fifth power, you'd have you'd have some sort of a chain rule or general power rule if you want. That's going to make things a little messy, because you're going to have sine, then cosine. It's not going to simplify out for you very nicely. You typically pick the inside of something without the power. So we're going to pick sine of 2x. Now, you got to kind of remember how to take derivatives of sine of 2x, because a lot of people here forget one thing about this. Do you see that sine of 2x is actually a...
Negative.
No, it's not a negative.
It's a general.
It's a chain rule.
Oh, it's chain rule, the general
Chain
power rule or whatever.
du equals... Here's how you do chain rule. How do you do chain rule?
You take your sine, flip the cosine of 2x, multiplied by dd of x of 2x.
Okay, cosine 2x, absolutely. But then the derivative of the inside must also be there. You see, when people do this, a lot of times they're off by a factor of 2. Actually a factor of 1/2, because when you divide it's 1/2. But they're off by that. They're off by a factor of 2. Because they forget all about the 2. Do you see the 2? Don't lose the 2. Okay, so we're going to have du equals cosine 2x times 2 dx. Otherwise, I'd probably write it as 2 cosine 2x dx. That's the appropriate way to write that. Just don't lose the 2. It's a chain rule. You got to have the derivative of 2x somewhere. The derivative of 2x is the 2. Move it out in front of your cosine. So what we're going to get is du, once we solve for dx, it's going to be kind of obvious that we picked the right choice. And here's where you'd make that judgment. By the way, you're getting more practice on substitution right now too, right? It's kind of nice. Do you see anything that's going to cross out? That's where you make your judgment. You go, okay, if this becomes a U, I'm good to go. If this gets crossed out, that's fantastic, and I'll be left with no more X's, and that's exactly what we want. Feel okay with this so far? Now, at this point, we're also going to change our bounds. We're going to change our bounds. Because I don't know about you, but I'd rather deal with the bound changes now and then just have to plug in some numbers rather than change everything back to sine of 2x and then have to plug in numbers and then figure out sine of that again. You follow me? We don't want to have to do that. So when we have x equals pi over 8 and x equals 0, let's figure out what those things are. Some of you guys are zoning out. Don't zone out. Stick with me here. You use your u substitution, you plug your x in, and you figure out what u's value is. So here we'll have sine of 2 times x. Well, x in this case is pi over 8. How much is sine of pi over 4?
Square root of 2 divided by 2.
Very good. Absolutely right. You guys okay with the root 2 over 2? Awesome. Let's do the 0. I'll take care of the 0 for you. Sine of 2 times 0, I love this one. That's sine of 0. Sine of 0 is 1, right? Good. Just checking. I was really checking there. Yeah, it's 0. Sine of 0 is 0. So do you know your new bounds? Let's do the substitution. Let's do it correctly. Let's substitute everything we can. We'll substitute for dx. We'll substitute for the sine of 2x. We'll also substitute for our bounds. So here's how the integral looks when we've done all our substitution. We go from where to where now? Where do we start?
0.
0 to where?
Root over 2.
That's because we're going to change all this stuff in terms of u. That's why we did our changing bounds. Okay, is the sine of 2x to the 5th power still there? Can you please tell me what I have instead, people on the left? U to the 5th. Not just u, but u to the 5th. That became a u? Yes. U to the 5th. Do I still have the cosine of 2x there?
Yes.
As of right now, yes. Do I still have the dx there?
No.
No, that's our substitution right here. We're going to do du over 2 cosine 2x. By a show of hands, how many people feel okay with this so far? So far. Good, that's almost everybody. Okay, tell me some nice things that happen. What are we going to do?
Cosine cross out. You can pull your 1/2 out.
Right there, you know for sure your substitution worked. You have nothing but u's. You've already done your bound change, that's great. And do what else?
Pull your 1/2. Pull out 1/2.
Great, the 2's on the denominator becomes a 1/2, I like it. 0 to root 2 over 2 du. Now that is a nice, easy integral. The numbers you have to plug in aren't all great, but that's okay. Just plug them in. So take our integral, we're going to get, don't forget about that 1/2. 1/2 u to the 6th over 6. I'm going to make this nice and neat before I evaluate. I'm going to get u to the 6th over 12. And do I have to plug in the x back into this thing before I evaluate? Why not?
Because you've already taken care of
I've
it.
already changed my balance. That's exactly right. Okay, so root 2 over 2, we're going to plug that in first, then we'll subtract and plug in 0. So root 2 over 2 to the 6th power over 12 minus 0 to the 6th power over 12. What's 2 to the 6th? It's how much? 2 to the 6th is 64? Now, root 2 to the 6th power is 2 to the 3rd, it should be 8. So you got 8 64ths there as well?
This one, it's what, 2 to the 4th?
Yeah. Root 2 to the 6th?
Isn't it 2?
8. Because it.
Eight.
It's 8 divided by 2.
It is 8, right?
Yeah.
That's going to be 1 8.
It's good, yeah, 1/8. Yeah. It's,
Am I way off or am I okay?
no, you're right. You're good. The first
Making
one
sure.
is 1/8 and then minus, yeah.
1/8 over 12 over 1.
96.
Reciprocate and multiply?
196.
Okay, what I'm asking you, are you okay up to here? Are you okay up to here? After that, use your calculator, do it. I did it because it's square root of 2 squared to the 3rd. So square root of 2 squared is 2, then 2 to the 3rd is 8. That's how I did it. And then 2 to the 6th, I had to have help with that. That's the 64, and then you start simplifying that. But that's the way you'd probably do this without a calculator. How many people understood what we just talked about? Feel okay with both methods? You can do it without changing bounds, right? That's pretty basic. Just make sure you sub in before you evaluate. Now changing bounds, a little bit more advanced of a concept, but it makes things easier sometimes. Nice doing this off to the side. You have to really worry about it, and then you just use your U. Just make sure you don't. The worst thing you can do is substitute back in for X here and then evaluate with your terms of U. That does twice the work with no reward. All right, let's continue a couple examples. Like I said, we got maybe 2 more to do. I'll show you how even and odd functions can play a role in calculating some integrals, sometimes very nicely. And then we'll get on to how to find the area between 2 curves. And you're going to find out that it's just a small extension about what we've been doing so far. Kids ready for today? Let's do this. So, looking at our first example, we got the integral. Of course, we're talking about a definite integral, so think in an area. From 2 to 5 of 2x minus 5 and x minus 3 to the 9th power. Now, does that fit your integration table? In order to make it fit, you'd have to distribute the x minus 3 to the 9th, and then foil, first outside, inside, all that. Not just foil, but anyway. Several times until you got this huge polynomial, then take the integral of each piece, which would be fine to do. It would take you a long time, but it is possible. And then you plug in the numbers to every single variable. That'd get a little tedious, right? So if that's the case, when it looks like that, you're probably going to try a substitution. Now, one is not readily apparent because what I've told you about substitutions is usually, the derivative has to be up there somewhere, right? It's got to be. If not, you need to manipulate the substitution somehow. So let's go ahead, let's pick a substitution, the one that you probably want to pick right now anyway, and then let's see if it works for us, okay? So pick a substitution right now. Go for it on your own. Using what I've told you, pick a substitution. Is it 2x minus 5 or x minus 3 that you picked? Good. Including the 9th power or not? No, it's usually just the thing inside the power that we take. Okay, well that's all well and good. U equals x minus 3. What do we do after that? This is pretty easy in this case. Du equals dx. Hey, that's nice. That's a direct substitution from du to dx. However, when you look at the problem, we go from 2 to 5. We're going to change this in a second, by the way. I just want to make sure the substitution is going to work before I start changing bounds and doing things like that. I don't want to waste any time. I still have a 2x minus 5, and here I'm going to have a u to the 9th, and my dx will be a du. U to the 9th, got it. Dx is du, got it. What's the problem?
There's still an x.
That's the problem. You have a du, but you also have a u and an x. And these are still in terms of what? Those are in terms of x. So if we can make the substitution work, I'm going to go back and change the bounds. But I want to make sure it works first before I waste that time. You got me? When this happens to you, and it will, when it happens that you make a substitution and you know you made the right one, yeah, if you made this one, that certainly wouldn't work in any way, shape, or form. But if you know you made the right one, you go, wait a second, that's not falling out of my integral anywhere. Sometimes, not all the time, but sometimes it means that you have to manipulate the substitution to solve for x and substitute in for x. And that's sometimes what it means. So when we have, especially when there's no power or anything, you can do that oftentimes, and we'll be able to distribute later. So it says, okay, u equals x minus 3. Can you solve that thing for x? How would you do it? Very good. Then what you say is, all right, then x is u plus 3, correct? Now we can make the substitution. Instead of x, hey, what else could I write?
U plus 3.
Let's do that. Then it changes everything into u's. So our integral, I'll do the bounds in just a second. Our integral is 2, what else?
Parentheses, u plus 3
I like it.
minus 5. And all that out. Yeah.
Big old bracket because you're still multiplying by u to the 9th. Well, let's see if we can all follow that. Do you see where the u plus 3 is coming from, ladies and gentlemen? So we're using the substitution we just made to solve it for the other variable, solve it for x. That way we can substitute that in, and it changes everything into u's, and that's great. So we change that into a u. We have 2, that's u plus 3. And then minus 5. The whole thing still being multiplied by u to the 9th, so I still have to have that bracket. Now at the same time, since we're now all in terms of u, now's where we probably will at least change our bounds. That'd be a good thing to do. So why don't you go through right now and change your bounds for me. I'll do it on the board as you're doing it, but make sure you can do it. Don't just follow what I'm giving you. I'm pretty sure I got 2 and negative 1. Did you get 2 and negative 1? All right, so let's change our bounds down here. Instead of going from 2 to 5, we know that if we plug in 5, we're going to get 2. We know if we plug in 2, we're going to get negative 1. So that changes from 2 to 5. That makes it negative 1 to 2. Now, a quick question just to refresh your memory. When I get down to the very end, am I going to have to substitute back in for x or not? Because now we're in terms of u, and that makes it nice. So at the end, we're just done. We just have to plug the numbers in. That's why we changed the bounds in the first place. Okay, hey, what next? Come on, we're on a roll. Before, I don't want to integrate right
You
there.
want to simplify all that.
Yeah.
You want to distribute out your 2, and then add minus your 5, and then multiply by u to the 9.
Yes, we call that tedious algebra work. 2u plus 6 minus 5. Then u to the 9th du. 2u plus 6, and then minus 5. Okay, well, that means we'll have 2u plus 1. Tell me something about this integral, what I absolutely have to do in order for this to work. Got it. I cannot just integrate the way it is. We found out that we can't separate integrals by multiplication. The only way to accomplish this is to distribute, and then we do the integral piece by piece. So when we distribute, please note that we're going to have same bounds, of course. We'll have 2u to the what? And very good. Du. Hey, that's a whole lot easier. That's a whole lot easier to integrate than that one. That looks almost impossible. If you didn't have this to follow, you go, wait a second, that substitution won't work. Try one anyway. See if it will work. See if you can manipulate like I did. And then maybe it will. If that's the case, shoot, it makes it a whole lot better to work with. And your bounds are even changed, so that's even nicer. So now we're going to integrate. Let's go ahead and integrate, and then we'll evaluate. So our integral is 2u to the 11th over 11. Plus u to the 10th over 10. Are you guys okay with the integral? Some of those integrals are pretty nice, right? Just take the basic stuff and substitutions. That's what a substitution is supposed to do. It's supposed to make your integral easier, not worse, easier. As it definitely does make it easier. Now what do we do? Good, because we changed the bounds first, we know that our bounds are in terms of u. Not in x anymore. These were in x's, those are in u's. So as soon as we get down to the very end, it's now evaluation time. Just make sure you evaluate very carefully. We're going to get 2 times 2 to the 11th over 11. 2 to the 10th over 10. That happens from when we plug in the 2. You got to plug it into both those terms. It has to go to both of them. So this piece right here is just the 2 evaluated. Are you all right with that so far? Yes or no, ladies and gentlemen?
Yeah.
Okay, then what do we do? Subtract, all right, you gotta do that. And we'll plug in the -1. 2, -1 to the 11th over 11 plus -1 to the 10th over 10. Oh my, how much is 2 to the 12th? Because that's what that is, that's 2 to the 12th.
2048.
2048? Okay, I'll believe you.
It's 4,096.
4,000. I meant 2 to the 12th, not 2 to the 11th, 2 to the 12th. 4,096? Okay. Because 2 to the 12th, 2 times 2 to the 11th is 2 to the 12th. So you either do 2 times 2 to the 11th times 2, that's going to give you that, or just 2 to the 12th gives you that. Plus 2 to the 10th.
1,000.
Yeah. Okay, all right. Minus, well, 2 times 1, -1 to the 11th. -1 to the 11th. Just -1. You got the odd exponent up there, it's going to be negative. So this is -2/11ths. That, though, that's a negative to the 10th power. That's going to be +1. So this will be plus 1/10. I'm going slowly so you see where all these numbers are coming from. Can you follow the fraction work? I know fractions are not your favorite thing, but it's Friday, right? What happens on Friday? Fractions, obviously. It's Fraction Friday. Okay. So we've got 4096 over 11 plus 1024 over 10 plus 2/11ths minus 1/10. So far, so good on sign changes? All right, we'll combine some like fractions. We got 11ths and 11ths. That's going to give you 4,098 11ths. That's going to give you 1,023 tenths. And then you're going to find a common denominator. All right. Which is?
110.
Probably, yeah, 110. I don't want to do that.
It's 52,233 1/10.
Wait, 52,000
233
over 10, over
1/10. That's the simplified fraction.
2,233.
over 110. Yeah, that's it. Awesome. I mean, that's easily relatable, right? Now, of course, what is this that we just found? Don't get confused with all the mumbo jumbo. What are we doing? That's an area. Could you find a decimal equivalent for that? Yeah, if you had to actually give an approximation for area, you could do it. That's the area under this curve between those numbers. That's what that's doing. How many people feel okay with that? Your calculator will do a lot of the fractions for you, so don't let that hold you back. If you can get it down to here, your calculus is done. Evaluation, that's Actually, pre-algebra, you're doing all that stuff now. The numbers in pre-algebra aren't that big, but you can do it. You ready for one more? Yeah? Any questions on this one before we begin? Your face says question.
Well, yeah, I'm trying
Your
to.
mouth doesn't.
I got to that point where I messed up my evaluation, and I'm trying to figure out what fraction I screwed up.
Got it. I'm going to say that's on you.
Yeah. I'm going to.
He needs likes.
Okay. 5, 2 plus minus 5.
Okay, granted, this one doesn't look fun. It really doesn't look fun. It looks fun to me. I love this stuff, but maybe not look fun to you. Why does it look fun?
Trig.
Yeah, trig always throws you guys for a loop. You go, oh, trig, seriously? Oh, I hate trig. Too bad. Second, it goes, man, it's not just an x in there, which is actually fortunate because you wouldn't be able to do the problem if it was. But it's a pi over x. And then it's over x squared, so there's a lot going on. It certainly doesn't fit the integration table. One question I have for you that's going to kill me if you get this wrong, my head's going to explode on the camera screen. And then no more videos, so don't do this to the people at home watching me. It really sucks. But let's see. Can you combine this with this?
No.
And get, oh good. Good. It's not cosine of pi over x cubed, right? Right?
Yeah, it is.
Head gone. No, it's not. It's not that. Then you'd get cosine of pi. That'd be a very easy integral. That's not the case, though. This is an angle over a function of x. That's what that is. So we have to somehow use a substitution. That's the only thing we have in our arsenal. Right now we have direct fit or substitution. Later on you'll get a lot more. Okay, that's your next class. But right now that's the two things we can choose from. If it's not a direct fit and we can't combine things like we cannot do here, then it has to be a substitution for us to even do it. If a substitution doesn't work, then we are SOL, sorry, out of luck. You can't do the problem. Anyway, let's go ahead and let's look for a substitution then. True or false? The substitution should include the cosine. True or false? Why? Because then you take a derivative of the cosine, right? And that would give you negative sign. Does negative sign appear up there? That is probably not the right choice. True or false? The substitution should be pi over x. Pi over x. Why not x squared?
Because it's not, it's not inside anything.
It's not inside anything. That's a good place. That's a good reason. Also, when you took the derivative of x squared, it'd be 2x, right? You know, and this is why I asked this question, that this is an angle. No matter what you get, you cannot cross that x out. You follow me? You can't touch it. Can't touch it.
Angles.
No hammer bats today. We can't touch that with anything. So even had you taken that as a u, it still wouldn't simplify. You cannot go inside of that cosine like that unless you have one of the like double angle, half angle, Pythagorean theorem identities to break up things. You cannot do it. And so the only option we even have is pi over x. So take a substitution of u equals pi over x. Go for that right now. Take your derivative if you can. You know how to take derivatives. We've passed that portion. So take your derivative. Also, I want you to change your bounds right now. Notice to take a derivative, you have to do that. You got to bring that x up to the top to take that derivative. Did you do that? Unless you want to use a quotient rule, which you don't. Trust me. Pi is a constant. You don't want to use a quotient rule. This is not a product rule either because pi is a constant. It's like the number 4. It's like the number 2. You don't have that here. So we take a derivative of u we take a derivative with respect to x on this side, you're going to get what? Yeah, I'm going to do it in 2 steps. You see the negative pi, x to the negative 2 dx. Are you guys okay with that? How many people made it down that far? Raise your hand if you did. Good, at least you didn't forget how to take derivatives, right? So we need to know how to take a derivative. And now you're supposed to solve for dx, yes? Solve for dx. Maybe make it look a little bit prettier before you do that, because right now it's like confusing. What am I doing? Supposed to divide by x to the negative 2? You can, and then flip it up. But what this really says is du equals negative pi over x squared dx. Do you understand that that's the same thing? The negative pi stays there. The x to the negative 2 goes to the denominator of a fraction. Now you can solve for dx. If you solve for dx, probably multiplying by the reciprocal would be the appropriate way to go on both sides. Or you can do 2 steps, dividing by pi, multiplying by x squared. In either case, hopefully you can follow this one. You're going to get negative x squared over pi du equals dx. I need to see if you can make it down there on your own, because that's some basic algebra, but you've got to be able to do it. Nudge it if you can. Yes, guys on the left-hand side, yeah? Okay, so basically multiply by the reciprocal on both sides, and this is exactly what you're going to get. Also, I told you to change bounds. Where do you change bounds? Do you do it here? Where do you change bounds? Way up top, all the way at the beginning. So let's go ahead. We'll change our bounds. I'll do it right here in this corner. When x equals 3, we want to find out what u is. When x equals 1, I want to find out what u is. When x equals 3, u is supposed to equal pi over that x. So that would be pi over 3. That one was almost in the way, so I didn't want to confuse you. Pi over 3. Did you get pi over 3 as well? When x equals 1, u is supposed to be pi over x. So u would equal pi. How many people feel okay with this so far? Make sure you have these in the correct order. Make sure you map them correctly from x to u correctly. If you don't, you're going to get the wrong sign on your integral. So watch what happens here. When I do my substitution, what was x? Well, it's 3. What's the u that correlates with 3? Pi over 3. When x is 1, what's the u that correlates with x equals 1? Right now you'll notice something. Do you see what's technically wrong with this picture? It is backwards. That's right, it's backwards. It's going from pi to pi over 3. That's pi to pi over 3, which says that if you want to, you can interchange them, but it's going to make your integral negative. I can guarantee you this integral is going to end with, well, I can guarantee you this integral is going to end with a negative area. That's what it's going to do. So, and that's because of that relationship right there. So the reason why I said be careful is because if you go, oh yeah, integrals always go from pi over 3 to pi, then you're going to miss that negative. You had to write like that first because the 3 maps to pi over 3. The 1 maps to pi. That's what those bounds were. You can't write them backwards just because you want to. Okay, that didn't work. We got to really be careful on that. And if you're going to switch them around, then you're going to have that negative up front. Okay, now for the other good stuff. We have, what else is up here? Come on now. Cosine still there?
Yeah.
If it's not part of your u, it's still there. Cosine of what? U. X squared is still there for right now. Dx is definitely not there. Instead of dx, you're going to write what dx equals to. That's negative x squared over pi du. I do like that for you. Now, some interesting things are going to happen. Interesting things are going to happen. Some things are going to cross out, some signs are going to be pulled out, some constants are going to be pulled out. Let's see everything that happens here. Tell me one thing that happens.
Just cancel.
X words are great. If that didn't happen, you'd either have to manipulate that somehow like we did before, which would kind of be a PETA, a pain in the rear end, okay, you don't want to do that. Or, that's about it, you can do it. So, cross out your x squareds, that's great. What else can I move out in front of my integral?
You're negative, now you have negative 1 over pi.
Yes.
Times you already have a negative if you reversed them.
I'm not doing that yet.
Okay.
Let's see if we can all make it down there in our heads. Are you feel good with that so far? So just doing our substitution, we've simplified some algebraic things up here, moved out our constants, which is great. Now, this is in the wrong order, but right here that's going to look like it helps us a little bit. If I reverse them, notice I can change the sign, right? Put them in the correct order, I'm going to change the sign. So what this says is, let's go ahead and let's flip these bounds. When I flip the bounds, I'm going to get negative 1 over pi. My integral will change from pi to pi over 3 back to pi over 3 to pi. Cosine u du. Okay, I made that negative way too big. There we go. But you see the negative, right? Technically what I really should have is a big bracket around here. If you want to draw that, you can. But that negative is going to change. That's going to become a positive. So we get our 1 over pi from pi over 3 to pi of cosine u du. By the way, it's really nice that we changed bounds here, because otherwise we'd have to substitute back in for that. And it's a little bit more confusing. You have to figure out a couple things as you're going. It's nice that that's already done for us. What I'd like you to do right now, would you go ahead and do the integral? Go ahead and evaluate it the way that we've written it, the way that it's kind of nice for us, and then see what you have. Don't forget about that 1 over pi out in front. Remember, it's positive now because the negative gave us that positive. Oh yeah, by the way, the integral of cosine, sine or negative sine? Sine. Good. That would change your problem, right? Remember that the derivative of sine is positive cosine, so the integral of positive cosine is positive sine. No plugging in back for x's. We already changed our bounds. That's great. So we don't have to do this whole resubstitution thing. We don't have to do that. We've changed our bounds off the side. We were already in terms of u. That just means from right here, let's evaluate it. So we'll do 1 over pi. That's going to be out front. Inside we'll have sine pi minus sine pi over 3. Sine pi.
0.
Okay. Had to be stumped for a second, I don't know why. What? Oh yeah, had it in my head as something different. Sine of pi over 3, how much is that?
Square root of 3 over 2.
Good. Were you able to get that as well? Cool. 0 minus root 3 over 2?
Negative root 3 over 2.
Interesting. 1 over pi, negative root 3 over 2. put it all together, you're going to get negative root 3 over 2 pi. That's your area. Looking at your area, would you say that this curve is above or below the x-axis for most of this region? For most of this region. If it crosses, I don't know whether it does or not, but if it crosses, most of it is below the x-axis because our area is mostly below the x-axis. So area speaking, it's mostly below the x-axis. How many people feel okay with our example? Okay, that's the last one you get about direct substitution with their definite integrals and changing bounds. I'm going to show you some kind of tricks, some not tricks, properties of things you can use to make even and odd functions work for you sometimes. Are you sure there's no more questions on this stuff? Do you feel pretty comfortable with it?
Yeah.
Substitution, no problem. You already learned that. Now it's just changing bounds and being able to evaluate. I've given you some kind of nice examples that kind of illustrate that a little bit better for you. But let's talk about even and odd functions and how we can use them to our benefit sometimes. Even and odd functions and integrals. Let's talk about even functions for a second. Hey, tell me something. What do you know about an even function?
They're symmetric.
Oh, so say that again.
Symmetric.
Symmetric, yes. About what? Which x-axis? No.
Y-axis.
Well, yeah, it's the other one. Very good. That's what geniuses. Okay, we're not in Calc 3. Okay, yeah, it's symmetric about the y-axis. Dear goodness me. Yeah, that's what even means. X squared is an even function. X fourth, even function. X squared minus 2, even function. They're symmetric about the y-axis. That's one thing we know about even functions. Here's the definition of it, actually. Even function says that. That's what an even function says. I hope it makes sense on why that would work. It says you plug in a number or the negative version of that number and your height is the same. What that's going to do is make it symmetric about the y-axis. Notice that? Plug in 2, you get out 7, whatever. Plug in negative 2, you get out 7. That means it's symmetric. It's going to go up at the same rate on either side of the y-axis, and that's what this is doing. So it's this, and what it means is symmetric about the y-axis. Just make sure you know it's the y. Well, let's think about this for a second then. Let's suppose that if f is even, and I'm going from negative a to positive a. Go from negative a to positive a, taking the integral of f of x dx. If f of x is, let's go through the logic, okay? If f of x is even, what do you know about f of x?
Symmetrical about the y-axis.
Symmetric. So that means that when I plug in negative a and I plug in a, I get the same output. At any point between them, I plug in the negative and the opposite of that, I'm going to get the same output, right? Would you agree then that the area from negative a to 0 would be the same as 0 to a?
Yes.
If it's symmetric about the y, it better be. Because you're going to get a picture like this. I don't know what f of x is going to look like, but I know it's going to be something like this. Whatever this does, this is going to do the same thing on the other side. It's supposed to look the same, by the way. I'm not that good of an artist. My paper looks better. I should show you my paper.
They're laughing at you.
They're laughing at my picture. Hopefully you can't hear that in the video. They're laughing at me. Well, if it's even, you're going to get that relationship. If you're going from negative A to A, that's actually a special case, right? It can't be going from like negative B to positive A, because those numbers wouldn't match up. That would be different. But if it's going from negative to positive the same number, well, then you know this area has to equal this area, which means that this integral is going to equal that integral. Does that make sense? Sometimes it's easier to calculate from 0 to a number than it is from negative to a number. It's easier to do that. So if we can do that, well, then no problem. If it's an even function, shoot, we can do this. We can calculate 2 times that integral, and we're good to go.
0 is always easier than.
0 is normally very much easier. Yeah. Now, if you have to use a substitution, the 0 might change, but normally 0 is easier. Let me just show you with an example that this does actually work. The only thing you got to do, which kind of stinks, is that you have to prove it's even before you can do it. Right? You can't just say, I think it's even, let's try it. No, that doesn't really work all the time. So you got to show that it's even. So for instance, let's talk about that one. Now, that's a pretty basic integral. You could clearly do this integral just the way it is. You could just do it, and that would be just fine. I'm not going to give you a super tough one where it's super, super nice to do that. I'm just going to show you with one that's easy for us to see that it is possible. First thing you do, though, you got to prove it's even. Here's how you prove it's even. You start out with f of negative x, and you have to show that that's equal to f of x. So f of negative x says this. You go to your function f of x, and you just replace x with negative x. So for us, that would be negative x squared plus 4. Do you see how I just replaced the x with the negative x? And then you work it down, you see what you get. What's negative x squared?
X squared.
Plus 4. What's x squared plus 4? That's f of x. That's exactly what I have back here. Right there, that proves it's even. If you start here and you end here, that means you have an even function. Oh, you'll feel okay with that one so far. Okay. What that says is that instead of doing this integral the way it is, I know that this is going to equal 2 times the integral 0 to 3. Not that. X squared plus 4. I'm going to let you do that the rest of the way out. What you would do here, take your integral, evaluate it from 0 to 4. No. Nope, no you wouldn't. 0 to 3. Go from 0 to 3 and then multiply that by 2. Has anyone done that already? Why don't you work on it? Let's see if we can get a couple of the same answers up here. Are there any questions on the even part of the board before I erase it? Did you understand the concept? Even means subtracting about the y. You prove it's even, that means the area on the left and the area on the right will be exactly the same. Therefore, you go from 0 to a, whatever that number is, and multiply by 2. Just be very careful. These numbers absolutely must match up for this to work for even functions. If that was a negative 4 and that was a 3, all bets are off. You can't do that anymore. I have no idea. Wow, plugging in the 0 is a whole lot better than plugging in that negative 3, huh? That's nice. That really is nice. Make sure you have parentheses there if you're going to do it. 9 plus 12 times 2, 21 times 2, 42? 42. Do that, 42. This I think it is. 3 cubed over 3 is 3 squared. 3 squared is 9. 9 plus 12 is 21. 21 times 2 is 42. So, cool deal. Did you get 42 as well? Awesome. So, it makes it a little bit easier since we're plugging in 0. Now, odd functions. What do you know about odd functions? They are symmetrical. Very good. Across the y? No, that would be even.
It's the opposite of even functions.
Not the x.
Across the origin, origin.
If they were across the x, wouldn't be a function. Think about that.
Across the y equals x.
No, that's an inverse. Darn it! Darn it, what is this darn thing? I don't know.
We guessed everything else.
No, you haven't.
Origin.
Origin, exactly right. It's symmetric about the origin, which means that it's a basic rotation of 180 degrees about the origin. So it says, well, it says this, actually. It says when you plug in negative, you get negative of the function. It says this. When you plug in like -3, it's going to give you some value. If you were to plug in 3, it's going to give negative of that value. So it's going to take it from up here and move it down here. That's a rotation of 180 degrees, or a what they call symmetric about the origin. So that is the definition of odd, and what it means is it is symmetric. But it's symmetric about the origin. Not in the axis. Origin. Let me give you the picture before I even do this. Here's what an odd function would normally look like. X cubed is an odd function. X to the 5th is an odd function. That's an odd function. Thank you very much. I know. I was genius. You know what? Maybe I do a little bit different here for you. It's easier to see this way. That would also be in, let's pretend that's an odd function. A little bit easier to see here. Let's say I'm going from -a to a. Tell me something about this area and that area if it's an odd function and symmetrical about the origin. Tell me something about those areas.
So it's going to be 0.
Wait, explain something about the areas first. This and this.
They're exact same.
They are the same area. Would you agree on that? Since it's symmetric, they have to be the same. It's a rotation of 180 degrees. That is the same. Now, tell me something about net signed area. Why 0? What net signed area says take the area above and the area below. The area above is positive, the area below is negative, and see how much change you have, and here would be 0. There'd be 0 net area out of this thing. Does that make sense? That would be for net area. If it asks for total area, it'd be exactly the same as an even function. Yeah, it'd be this times 2, just like an even function was for total area. Now, a definite integral does not automatically calculate total area. A definite integral automatically calculates net signed area unless you have what in there? Absolute value. That's exactly right. So, what this says, if your function is odd, an integral is going to calculate the net signed area. Therefore, if you have an odd function, if f is odd, and I'm going from -a to a. Notice that those numbers, they have to be the same. Do you see why they have to be the same? If I go just a little bit closer right here, are the areas the same anymore? Clearly not. So they have to be the same. But what do you know? If you're going to take an integral of an odd function, which is symmetric about the origin, and you're going to go from negative a to a, which says where you end is exactly the same, but opposite, it means your area is going to be exactly the same. How much is that integral?
0.
Oh, shoot, that's nice. Do you even have to do the integral? No. No, that's a beautiful thing. Not unless I ask you for total area. If I say total area, then this is what it does. This is above and beyond what the book does right now, but if I ask you for total area, then it would be this, right? And what that would be is, because they're equal areas, you'd have 2 times 0 to a, just like you had in an even function. It basically, think about what it would do. Just think for a second what absolute value does. Absolute value pretends that anything below the x-axis is above the x-axis, right? So absolute value, I hope this makes sense, absolute value would go, what's that do? Changes from odd to even. See it? Kind of cool, right? And then you have exactly the same thing for even function. That would be for total area. If it's just like this though, given to you just like that, that implies net signed area. That means the areas are the same but on opposite sides of the x-axis. That means the area is equal to 0. Hence the integral would be equal to 0. Would you like to see one application of this? Sure. You're going to like this. You're going to ask for 30 of these on the test. Well, maybe not. Maybe 5.
Are we gonna get it?
You can always hope.
One question of this one, expectation leads to disappointment. So this is a one question test
Right.
one person.
Never mind, we lied. We don't want that on there.
No, you don't. The thing about using these properties is that you have to prove that you can. You can't just say, I think I can, therefore I go. Because all of those would be 0 for you guys. You'd be like, oh, negative 3 or 3. 0! Oh, I'm awesome. No, you're not awesome. Well, I mean, you might be awesome, but not at that. You got to prove that it actually works. Just like you had to prove it was even, you have to prove this was odd. Now, this says I can do a lot of integrals that otherwise I couldn't do. Do you see why it says that? It says, my gosh, I mean, do you know how to do that integral? I don't right now. I mean, just looking at it, I'm thinking trig substitution, but you don't know trig substitution. You know substitution, you know use substitution. So that's off the table. No matter what you do with the substitution, that is not going to work. Take 1 plus x squared, derivative is 2x. That doesn't appear. Take sine x, there's no cosine. You're stuck. The only thing you can do is say, well, it's going from negative 3 to 3. Let's see if this is even, or let's see if this is odd. If it's even, we're probably stuck anyway, because they still can't do the integral. Even doesn't get you away from the integral. Just says, I can multiply by 2 and have a 0 in it. That's nice. Odd gets you away from the integral. That's even better. So let's try to see if this thing is odd. What you do is you start out with your function. That's what we're trying to get to, but maybe have a negative in front. And you say, what I want to have is I want to plug in negative x, and let's see what it does for us. So take everywhere you see x, and see what happens. So negative x, negative x. Well, if I do that, this actually isn't that, it looks bad. It's really not that bad. Square root of 1 plus negative x squared, how much is that? Wait, minus x squared or plus x squared? Okay. Does anybody remember anything about sine of negative x? Yes, that is a property. It says sine of negative x is the same as negative sine of x. If you don't believe me, look it up. That's a true statement. Sine is, when you think about it, an odd function. It is inherently an odd function because it does this and it does that. It's symmetrical about the origin, right? So knowing that sine's an odd function says this absolutely must be the case right there. Sine of negative x has to be negative sine of x. It will work out for you. So that's true. Well, look what we can do. This is equal to negative sine x over the square root of 1 plus x squared.
Which is what you need.
Yeah, this right here, this is f of x. So this is negative f of x. So right there, is it odd or not?
Odd.
If this happens, it's definitely odd. What's not so odd, which is awesome, is that we can just do this and go, how much is the integral? 0. Sweet. Didn't even have to do it, it's 0. How many points have we talked about today?
Yeah.